Okay, so we've just discussed limit theorems for laws of limit laws for sums of independent and identically distributed random variables. And what we have found is that the distribution of the sum properly centered and normalized is independent of all the details of the initial distribution. Okay, so this is a form of what is called universality. So, which is the fact that the distribution P star of X does not depend, is independent of details of the original distribution P of X. So, for example, in the central limit theorem, we have seen that the limit distribution is a Gaussian, whatever is the distribution of the original variables, as long as the variance is finite. So this means so the picture that one has is that in the space of distribution, so when one considers sums, when one considers the random variables yn minus an sn, which is the sum properly normalized, so one starts from an original distribution P of X, and the distribution as n increases, the distribution of the random variable y changes, and it converges to a particular distribution P star. And and if you start from a different distribution, you end up on the same asymptotic distribution P star. So I would like to discuss how this behavior happens. And the idea is the following, so that the sum, which is the sum of n random variables, actually can be done also in different ways. So, for example, you can sum variables in pairs. So define this as the sum of two variables 1. Then you have another sum of the third and the fourth variable. You call it S2, etc., until S2 of n over 2. So you can sum n over 2 sums of sums of two random variables. So actually you can sum also these variables in pair and continue. So essentially you can write this equivalently if you sum 2 to the k random variables, and then you can compute the original sum as the sum of n divided by 2 to the k of these random variables. Okay, so and as n goes to infinity, you can continue this process of merging two variables in pair. So, and each of these variables is the sum of two random variables at the previous level. Okay, so then this means that but if we want to discuss the distribution of yn, then we need also to rescale and center this distribution. So we need to look at variables y, which are at a certain level 2k, or let's say just k, say k plus 1, which are the sum of two random variables at the previous level centered and normalized. So, for example, you can choose A in such a way that the probability that yk is less than 0 is equal to the probability of yk being larger than 0. And you can choose B in such a way that the probability that yk being smaller than 1 in absolute value is equal to 1, okay? So this is one way of choosing how to center and how to scale your variable in such a way that the scale and the location of your distribution of the variables y is always the same. So then the distribution of your random variables at the level, at the step k plus 1 will be just given by the integral dx1 dx2 of p at level k, the variable x1, p k variable x2 times the delta function of x minus x1 plus x2 minus a divided by b. Okay, so now the question is, so the problem of finding the limit solving our original problem is equivalent to the problem of finding A and B such that P of K converges to a distribution P star as K goes to infinity. So K goes to infinity is equal to the limit when n goes to infinity in this case. So in other words, the distribution, so if you write this relation here as a recursive relation that gives you pk plus 1 in terms of pk, then p star is given by the equation, the fixed point of this transformation. Okay, so this is a transformation that gives you the distribution of the original random variables. So the original random variables at a particular level k in terms of the random variables at the previous level. Okay, so what are the properties of this transformation? So first of all, you notice that now the solution of this equation for P star has no details, does not carry any detail of the original random variables. The second thing that you notice that now if you look at how what should be your value of Bn when you perform k of this transformation where you group two variables, then Bn should be the product of all the, so this Bn should be the product of this B star, which is the value for which that correspond to the solution of the fixed point. So this would admit solution a fixed point which is non-trivial for certain values B star and A star in this relation. And so the Bn would be just B star to the power k, multiplied k times. So you can rewrite this as n to the power alpha, where alpha is the logarithm base 2 of B star. So you see that in general, as a consequence of the fact that of this picture here, that when you look at the sum of many random variables, you can think of this as the evolution of probability distribution under the operation of a sum. So the consequence of the fact that there exists a fixed point is twofold. So on one hand, you find that the distributions are universal. So the fixed point of this solution is independent of the original distribution from which you start. And the second condition is the second consequence is that generally you expect that the scaling, the way in which you should scale your random variable takes a power law behavior. Okay, so this is essentially very reminiscent, or is the same type of structure that one uses in statistical physics to study the behavior of systems at a critical point, where essentially, so the system at the critical point is a system where, say, you have a physical system which is that can be in a ordered phase for T less than a critical temperature, or in a disordered phase when T is larger than a critical temperature. And right in the middle, so for example, if you look at the magnet, a ferromagnet at low temperature will have all its moments in the same direction, whereas at high temperature, all the spins will be aligned in different directions. And so what you have at the critical point is a particular situation where the properties of the correlations in this system are such that the arrangement, the spatial arrangement will be scale invariant, in the sense that if you look at a particular subsystem and you scale up to the whole system, you will see a configuration that is statistically independent from the one of the whole system. So, so the mathematics that one used to describe this particular point, this particular systems, is exactly equal to the ideas that we discussed right now for limit laws in for the sum of independent random variables. And the idea is that one should connect the distribution, the description of your system at different scale by what is called a renormization group transformation. And this consists of two steps. One is coarse graining. And coarse graining means essentially summing together. So you can get the description of a larger system by summing the description of the smaller system. And the second step is rescaling. And so the point I want to make is that the limit laws of sums of independent random variable is the simplest example of where you can see these ideas of the renormalization group at work.